In today's video, let's discuss about how to deal with more than two continuous random variables by using three-dimensional probability density functions f of x1, x2, and x3, such as when we consider height, weight, and blood pressure. So this triple integral is used to find the joint probability of these three variables falling within specified intervals. The function f of x1, x2, and x3 represents the joint distribution of three continuous random variables. So these density functions shows how the probability mass is distributed across three-dimensional space, with each dimension corresponding to one of the variables, height, weight, and blood pressure. So let's try to compute the joint probability that each variable falls within a specified range. Let's try to perform a triple integral over these respective intervals. So this process accumulates the infinitesimal probabilities across the defined volume in this three-dimensional space. So its mathematical expression is probability of A is less than x1 less than xb, and C is less than x2 less than D, and E is less than x3 less than F, which is equals the triple integral from E to F, from C to D, and from A to B of f of x1, x2, and x3 with respect to x1, x2, and x3. This triple integral integrates the probability density function over the intervals for height, weight, and blood pressure, which providing the probability that all these measurements fall within these specified ranges simultaneously. So this is a very simple example as a joint probability density function use Gaussian distribution, which show a conceptual representation of integrating over certain intervals for each variables. So we project a three-dimensional distribution into two-dimensional slices, as true three-dimensional density visualization can be very complex and less intuitive to interpret directly, right? When we try to compute the joint probability for specified ranges across these three variables, we would calculate a triple integral over these respective intervals. So this operation sums the density over a defined volume in this three-dimensional space. So this formula represents the total probability of observing values within these specified ranges for height, weight, and blood pressure simultaneously. It integrates the density of the box, which is defined by AB in height, CD in weight, and EF in blood pressure. So this integration process effectively sums all the tiny probabilities which contained within these multidimensional intervals, which giving a measure of how likely it is to find a subject within these specific parameters ranges. These plots displayed represent slices of three-dimensional joint probability density function for height, weight, and blood pressure, and each slice is taken at a specific value which is close to the mean for one of the variables, which shows the density distribution across the other two variables. So this helps us to visualize the concept of a higher dimensional joint probability density function and how these variables might interact in a multidimensional space. The first slice is at height is equal 6 feet, which shows the joint distribution of weight and blood pressure at a fixed height of 6 feet. It allows us to observe how changes in weight and blood pressure relate when height is constant. The second slice is at weight equals 170 pounds. This slice demonstrates the distribution of height and blood pressure at a constant weight of 170 pounds, which provide insights into the variability and relationship between height and blood pressure at this weight. And the third slice at blood pressure, which is equal to 120 millimeters of mercury. So this view illustrates the distribution of height and weight for a fixed blood pressure of 120 millimeters of mercury. So this helps us to understand how height and weight might correlate at a particular blood pressure level.